Okay, welcome to your 9.1 notes for direct and inverse variation. So the direct variation is a relationship between a y, a constant number k, and x. You should have seen this form before because it's nothing else than a linear relationship where k represents your slope. So k is your slope. And what we know about a line and a slope is that the slope is always constant. Very important to remember. We also need to remember that to have a relationship, k cannot be equal to 0. So when we look and imagine a slope and a line, as x increases, our y also increases. And as x decreases, our y will also decrease. Remember this form. When it's a direct variation, we're going to multiply the constant k with x to get our y. We're going to use this knowledge now to solve some of those problems. So, suppose x and y vary directly, important to know, and x is 3 and y is 15. We can use our direct variation model of y equals k times x, and we can plug in the information we know. Y is negative 15, k is 3, and we can solve for our constant k, which is negative 5. At this point I'm not done because I'm asked to find the equation that will model this direct variation. So I go back and I'm going to plug in my k into the form. Now I have an equation that will model this relationship. For b, what is y when x is 5? I can use the model that I've just found, and instead of x, I can plug in my 10. I can calculate out that y is negative 50. The inverse variation is kind of the opposite of the direct variation. So instead of multiplying our k by x, we're going to divide by x. Sometimes you will see it in the form where I rearrange for k. K is equal to x times y. This is the same, it's just rearranged for either solving for k or solving for y. In this case, as x increases, my y will do the opposite, y will decrease. And as x decreases, my y will increase. So it's inverse, it's doing the opposite of what is given. Using the form for inverse variation, x and y vary inversely with x is equal to 2 and y is equal to 8. I can use any of the forms for inverse variation, either this one. I could also use the one for k. In our situation, this one is much easier to use because I need to solve for k anyway. So I'm going to use this form. I'm going to plug in my x and my y. And then I know my k is 16. I then put it in the y equal form with 16 over x. This is now the equation that will model this variation. I can use this model to find what if x is 4. Then I can find y, which is 16 over 4, and therefore y is 4. Let's look at another example like this. So we are x and y are inversely, which means I know it is either the division by x or the form xy equals k. I have x and y given, so I'm going to use this version again. 7 times 4 equals k. K equals 28. Put it into the form to write the model. Y equals 28 over x. Here we go. Let's look at some other scenarios. This one asks us to write a model for the following scenarios. So what do we have? We have y that varies directly with the square of x. Remember, when y is directly to x, the relationship is the multiplication of the constant k and x. But this time I'm not just finding x, I want the square of x. So I'm going to add a square. Number 2, y varies inversely with the cube of y. I assume it was supposed to be x. Inversely means we're going to use the form where k is divided by x, but it's not just x, it's divided by the cube of x. Number 3, z varies directly with x and inversely with the product of y and w. This is a very long sentence with a lot of instructions. Just do it step by step, piece by piece. So what do we know? We know directly with x. So I'm going to write the first part of my equation. Z varies directly means multiplication with the constant k. But it also is inversely, which now means we're going to divide by whatever is coming. And it is the product of y and w. Here we go. Sometimes when I talk about two variables that are both directly in a variation with a third variable, I can use the word joint. So in this case, on number 4, when I say z varies jointly with x and y, what I'm actually saying is that z is direct variation with x, and it also is a direct variation with y. So instead of repeating direct variation twice, I use the word jointly. So I know that z is jointly direct variation, means multiplication with the constant k of x and y. Z varies jointly with x and y. I actually just found exactly the same thing in number 4. But now it is also inversely with w. So I'm going to take this whole deal and I'm going to divide it by w. Okay. Let's do the opposite. So I'm given the function or the equation and I'm to describe in words what we're actually doing. So our f varies. And now let's think what it does. So because m and a are both multiplied, so I know that f varies directly with m. It also varies directly with a. So I can use the word jointly. So f varies jointly with m and a. The next one, d. Because m is on the top, that tells us that it varies directly with m. And v is on the bottom, so inversely with b. KE, in cases when we just have to describe what we're doing, constant numbers, in this case the 1/2, don't have to be mentioned in the relationship. So we only have to talk about the m and the v squared, and because they're both multiplied, I know it varies jointly with m and the square of v. Okay. In this case, we are to find the relationship to be either direct, inverse, or maybe neither. If we do determine it is direct or inverse, we would have to write the equation that models the variation. So the first thing that you want to do is you want to find out how is your x behaving. In this case, your x is increasing. And then you check your y. My y's in this case are decreasing. So if one is increasing and one is decreasing, I'm quick to say, oh yeah, this is an inverse variation. But I actually don't know this yet. I have to prove this variation to make sure that all the relationship between x and y follow the constant k. So if you remember, your direct variation is y k over x, or the version x times y equals k, which is easier to use right now. So let's check if our constant k is the same for all of the ordered pairs. So 10 times 20, 10 times 2 is 20, 4 times 5 is 20, 5 times 4 is 20, and 1 times 20 is 20. So in this case, I've proven that my constant k is the same for all of them. I have x increasing, y decreasing, so I know this is an inverse variation, which I can now plug in to my formula. I already know what k is, and here's the model. Okay, x is increasing and y is also increasing. So, is it a direct variation? We have to check. I know that normally y equals k times x. If I rearrange to solve for k to check if my constant is the same, I'm actually checking y divided by x. So in this case, we have 2 divided by 1, which is just 2. 8 divided by 3, just have to leave it as a fraction. 20 divided by 7, and 29 divided by 10. We can see that all of the constant between x and y is different. They're not the same. So this actually is not a direct variation. It is neither. Okay, next. My x is increasing and my y is increasing. So I have to check, is it a direct variation? Check for the constant k. Y divided by x. 6 divided by 1, 6. 12 divided by 2 is also 6. 30 divided by 5 is 6, as well as 42 divided by 7 is 6. Because all constants are 6, they're all the same, I can now determine that yes, this actually is a direct variation. So I can put it in the form of y equals 6x. Next example, y varies directly with x and inversely with z. So directly with x means we have k times x. Inversely with z means we're dividing by z. So this is what I want to use to find the model for down here. If x is equal to 10, and this actually should be a z, z equal to 2, and y equal to 15, we can plug this information into our equation, and then we can solve for k. So we have times 2, and then we're going to divide by 10. K is 3. So my actual equation is y equals 3x over z. Okay, when x is 8 and z is 6, what is y? I'm going to use the equation I just found, and I'm going to just plug in the information I'm getting. 3 times 8 over 6. Y equals 24 over 6. Y equals 4. And there you go.